Okay, so I guess I'll get started. So my talk today, a gentle introduction to recursion schemes. So how many people here are familiar with, whoops, sorry, maybe I should quit Slack. So I was saying, how many people here are familiar with recursion schemes? So a few people, there's a brigade here of people that are familiar with recursion schemes. Great, I'm happy to hear that. So hopefully I'll be able to teach you something that you'll find useful. By the way, feel free to interrupt me and ask questions during the presentation. That doesn't bother me at all. Actually, it even shows me that you're listening. And actually, I put out a challenge. I have not compiled any of the code in these slides. So the first person that finds a compile error, I haven't thought about what I'll reward them with. But you'll get the glory of discovering a compile error without a compiler. So, okay, the outline today, start with a quick introduction to recursion schemes, then follow with motivation. And the reason why for me it's important motivation is, so I work at SlamData, and when I first arrived, on my first day at work, we already were using recursion schemes a little bit. And when I saw all these classes with Fs in them and kind of all this boilerplatey looking stuff around our around our data classes, at first I was like, whoa, what is this stuff? Like, what's the usefulness of this? And I was skeptical. I'm always a little bit skeptical of things. I want to kind of truly understand why they're useful before I'm willing to accept, the drawbacks. Oftentimes things have advantages and inconveniences. So hopefully I'll be able to motivate you. So motivate their use. So you'll keep listening to me for the rest of the presentation. I'll follow that with just a brief explanation of how it works, kind of under the covers. Follow that with more examples, and finally just briefly mention how you can use them in your day-to-day programming. Oh, whoops. Okay, so quick introduction about myself. My name is Remi Desjardins, but I usually go by JR here in the US. Usually goes over easier. My employer is SlamData, so I work with John DeGoes. I've been doing Scala for about 3-4 years, although it feels like longer. And I've been living in Boulder ever since I started working at SlamData. So recursion schemes were first introduced in a paper in 1991, 2 years after I was born. Functional programming with bananas, lenses, envelopes, and barbed wire. It's a paper that's not super well known out of functional programming, and it's even inside of the functional programming community, probably not as well known as it should be. But it's a really interesting paper that introduces a lot of concepts, including recursion schemes. And so recursion schemes, I would say, are like a way to generalize recursive algorithms, but that's just my way of thinking of them. Okay, so motivation. So recursive data structures are, fairly ubiquitous. I have a few examples here. They're useful for database applications, 3D graphics, file systems, compilers. I'm sure all of you, encounter recursive data structures pretty much on a daily basis. Some more than others if they're, writing compilers for a living. But I'm sure everyone does. Oh wow, there's 39 people. I just saw that on. That's cool. Looking at the slides. Right, so an example I really like is modeling a tournament, because I love sports. And ironically, I remember this one time I canceled late because I was sick or I had something else. I canceled 2-3 days before a tournament, and the organizer of the tournament got so mad at me because he was like, do you realize it takes me a whole day to take out names from a hat and build a draw, and you're screwing up everything because you're not showing up. And I remember that really stuck. I was like, that's ridiculous that there's no standard app to generate draws in like 5 seconds. And so it always really stuck with me, the example of like generating tournaments. So here's an example of a tournament. We have a bunch of players, or teams, whatever. And it's a simple elimination tournament. So the winner of player 1, player 2 is gonna play the winner of player 3, player 4, and that continues until there's a champion. So here's kind of the initial model that probably most people would reach for when modeling, this tree, this tournament bracket. So we have our participant, which is whatever, but right now we'll just model it as a string. That's not super important. And then something I'm calling a draw, and then a future match, which represents, a match here represents the kind of leaf nodes. So it's just 2 participants. And then our future match represents, any one of the nodes that are not leaves. So like that, the winner of that one would be a future match. So this is the traditional way of modeling a recursive data structure. So let's say we want to write a size function for this draw. It's pretty straightforward. Looks like this. We take in a draw. If it's a match, then the size is 2. If it's a future match, we call size on the left side, we call size on the right side, sum the 2 together, and that's the size of the draw. So pretty straightforward. Now, here's what I'm suggesting. This is how I'm suggesting you model this tournament instead. So it's a little bit more code at first. It's like, what's going on here? We still have our participant. Instead here, I postfixed this f at the end of every class. So we have our draw f, which now takes a type parameter. I'll flip to the question. We have the future match, once again, still takes a parameter. And the interesting thing here is our left and right, instead of being draws, they're a's. So we're kind of abstracting what's on the left and the right. And that extends draw f of a. And our match is also a match of A, but our match doesn't actually, it's a leaf node, so it's still just containing participants. And then for convenience here, we have this draw. We're defining draw as a fix of draw f. So I repeated that in case you forgot. So now that we have this model, what does our size function look like? It looks like this. So we get our draw. Now we can call this function called kata, which stands for katamorphism. And our pattern match looks like this. So if we get a match f, it's 2. That's the exact same thing as before. And if we get a future match f, and left and right, we sum left and right. Is there a question over there?
Is katamorphism reduced in this case?
Maybe. It's similar. I'm not sure it's exactly the same thing. And so what changed here is we actually don't have to call recursively size on the left and right. Sort of auto-magically, the left and the right here are ints. And so that might seem like not a huge deal. We're just getting rid of 2 recursive calls. But it kind of is a big enough deal. But in this example, it's not super... it doesn't seem, too crazy. So I have another example, which is a little bit more involved. Hopefully, you'll be able to follow. It's not too complex, but coming up with an example that actually really showed kind of where it's really useful was, and like super simple was not necessarily that easy. But maybe I could have. So I'm introducing here a function called probability of win, which takes a candidate and 2 participants, the candidate and over which that person is going to win, presumably going to win, and it's going to return us a task of float. So task is just like, it's a monad from, Scala Z. And, maybe it's like a web service that you give like 2 participants, it returns you the probability that the first one's going to win over the second one. And so we have this function, and we're trying to figure out who has the best chance of winning the tournament. So we take in a draw, and we're going to produce a task of participant because there's no like safe way of removing once you have a task of getting out of the task. So we're just going to return a task participant. They can do what they want with the task. So first thing we need to do, we need to define a recursive version of our function. It's going to recurse. It's going to accept a draw as well. And it's going to return a participant and a float. So it's going to return the participant that in that part of the draw has the best chance of winning. And it's also going to return what his chance of winning is. And so the first thing we do, we match over leaf nodes, over the simple matches. We've got our left and right participant. This is pretty straightforward. We just call chance of winning with the left and right participant. We map over our monad. We get the chance. If the chance is bigger than 0.5, then that means the left-hand participant has a better chance of winning. And if it's the right-hand side, the right-hand person has a better, well, if it's smaller than 0.5, then the right-hand person has a better chance of winning. We inverse the chance in order to get their chance of winning. That's kind of, pretty straightforward. The case that's a little bit more complicated is the future match. So in the case of a future match, we have the left-hand side of the draw and the right-hand side of the draw. So what we need to do, we need to call a recursive function on the left-hand side, best chance of winning. We get the result of that function. Unfortunately, yes?
You get a compilation error there for your last line. Chance of winning and that with some abstraction now.
Yeah, nice, you found it. Good job. So then you get the result of the left. And unfortunately, you can't pattern match in that because of Scala. It tries to, it would apply a filter to that, and I don't think TESS supports filter. So anyway, basically, we just have to deconstruct it on the following line. It's unfortunate, but it's just what has to happen. We get the left participant and their chance of winning. We do the same thing on the right side, and then finally we call our chance of winning function with the left participant and the right participant, and we get the chance of them, the chance of winning between themselves. And then what we can do, we can calculate the new chance of the left-hand participant by calculating his chance of winning the sub draw from where he's coming from times the chance of winning this particular match. We can do the same thing with the right-hand side, and then if the chance of winning the first part of the draw plus the chance of winning this match that we're looking at right now is bigger for left, then he's the one who has the better chance of winning this whole draw. So we return left part with the new chance, or else we return the right part with the new chance. Finally, we call this recursive function with our initial draw, and we discard the chance of winning. So that's what that looks like in the kind of initial model. Now, what does it look like with our fixed point style? So here's the fixed point. Here's the way we defined our model in the fixed point style. We still have our function probability of winning, and this is the new implementation, which is significantly shorter. So now all we need to do, we call kata m, or katamorphism. M stands for the function that you're giving can be a monadic function, and it's going to take care of binding. And so the case for our initial match is essentially the same thing. We don't have to call the recursive function no, it's essentially the same thing. It's the same thing, I think. But the one with our recursive node, that's the interesting one. So in this case, we can just pattern match, future match f, and then what we get inside of our structure is the left participant, their chance of winning, the right participant, and the chance of winning. So this way of modeling has kind of allowed us to get these things for free. There's just like, oh, great, like the sub draws the results are there. They're already accessible. I don't need to do all this kind of work to access them. So all we need to do is the last part of our algorithm, which is calculate the chance of winning of left versus right, map over that, calculate the new chance, and then figure out who is the new chance, who is the best new chance of winning. So I think that was an improvement. This is just the comparison in case you're interested. So basically what we notice is that whole first part, the whole for comprehension, where we're calling recursively our function, and that's returning us the result in task. So we need to extract it out, And then finally, you know, that part of the code is kind of like done for us in the background. So we just need to focus on what's inside the yield, which is really the interesting part, the meat of our algorithm. Yes?
Is there any particular reason why you're using tasks rather than just like, you know, M for someone else?
You know, I had it M in my slides at one point, but I just wanted to make it concrete. But yeah, no, it's totally any M, and I had M, but then I went back to task because, you know, I just wanted, you know, I don't know, to make it concrete or something.
So compilation error, your best chance of winning is acting like it's stupid with this task.
Say what?
Your best chance of winning is acting like returns of 2 returns task.
Right, yeah. Yeah, I mean, that's true. Okay, so a little bit of intuition. So what we're doing here by making left and right generic is we're allowing ourselves to build these things. Actually, there's another compiler there. It should be future match F. So we can build a future match F, and we can just put strings in it. I mean, answer strings. We don't need. So it's more general, right? We can put anything in there. We don't need to put ourselves, the recursive data structure. And so that allows basically the algorithm to, you know, put the things that are already calculated in the structures, so it seems more, well, it is more convenient for us. But the interesting thing that this brings up is so let's say we do want to go back to our, you know, ultimately what we want to model is recursive structures. And this draw is a recursive structure. So take a future match. A future match, if you want to instantiate a concrete future match, you need A to be something. And so, you know, if we're kind of thinking, okay, what's it going to be? Well, if we want it to be a recursive, it'll be a draw. But then the draw needs something else inside of it. So we stick a draw, and then we stick a draw. And basically, we kind of have a problem here because there's no way for us to describe a recursive data structure because there's always an A there. Every single one of these takes an A, so you need to give an A, and then what A you're going to give the draw again. And anyway, so you get this infinite loop. So how are we going to fix that? I'll actually get back to that problem. I'll just show one more example to motivate the use first. So what we were doing before was folds. So we're taking a recursive data structure and we're applying an algorithm and we're reducing it into a single element, an A of whichever type. So recursive schemes are also useful for unfolds. So here we have our initial model. And we're going to define a very simple function from list, which takes a list of participants and produces an optional draw. So this is our implementation. If the list is smaller than 2, then we can't construct a draw, so we return none. If it's 2 elements, then we return some match. And if it's more than that, we split the list in 2. We get the left-hand side, the right-hand side, and we call recursively from list on the left, from list on the right, and we construct a future match out of that. By the way, if there's some that are not familiar with this notation, that circle star is apply, so you can think of it as zip on option. So you're taking the left-hand side and the right-hand side, and if they're both sum, you get a sum. If one of them's none, you get none. And then, you know, if they're both sum, you apply the future match constructor to get a sum of future match. For those who's familiar with applicative, it's the apply of applicative, or app. So now what does this look like with our fixed point style? We have a from list, and this is the new implementation. So the first part is essentially the same thing. It's the second part that is more interesting because we don't need to recursively call our stuff. So we split our list in 2, we get the left and the right, and then we just simply construct a future match F whose A is a list. And we give that back to Anna M, and it takes care of that for us. So once again, just a little bit simpler. Here's the comparison. You can see that we don't have to use that funny symbol. We don't have to use it. So these are all the recursions. So we looked at catamorphisms and we used anamorphism for unfolding, and these are all the other ones. So there's a whole bunch of transformations that have names and are known. So you can use that to transform your data structures. And I think that just start by using kata and ana and then go from there. You can use a bit more fancy stuff later. Yes.
Can you go back one slide?
Yes.
So your recursive call can never return a none, right? Or your quote-unquote recursive.
Well, which one are you talking about?
Your last in the bottom, your last case. It's always returning a sum. So shouldn't it be able to return a none? Like if one of your branches was missing, if one of your leaves was missing a thing.
So if one of the leaves was missing, so because we're calling ana m, it's the ana m function is binding for us. So if there's any none, it's going to return none. So we're only going to hit that case XS if I just want to make sure I'm not right. Yeah. So future match F, we're basically we take our list, we're dividing in two, and then we're constructing our future match with the two lists. And then what that's going to do is it's going to basically call the function again with those new lists in order to get the subnodes. If anything in there returns none, then it's going to bubble back up and say, yeah, we can't do this whole thing, so it's going to be none.
Okay, so it won't directly be the result of the last case anyway. I see. Okay.
Yeah. And there's ana versions and ana m, and it's just because when in a purely functional code base you end up with monads a lot. So having monadic versions are convenient because you don't have to do the binding, and it does it for you. Any other questions? Okay, so I'm going to explain briefly how this is working. How many people think this is kind of this is a little bit magic? Okay. I think some of you are not being honest because I thought it was fairly magic for some reason. Okay, so how does it work? So remember our problem. How do we instantiate an actual draw, like a recursive draw? So it turns out the fixed thing we saw before is the trick. So we're fixing our draw f, and then magically we have a recursive draw. That's it. That's the explanation. So what does fix look like? This is what fix looks like. So I'm going to spend 10 minutes here staring at this with you guys. But seriously, it's a little bit. It's a little bit I'd say mesmerizing here. It's kind of magical. It's like, oh, we just fix the thing, and suddenly we have a recursive draw. So what's happening here is fix expects a type that takes that has a hole that takes a type parameter, and it has an unfix, which is our f, our draw, where the a is a fix of f, and so. Basically, kind of tricking the file system into you have basically two recursive data types, and together they make a finite data type, which is kind of interesting. So luckily, I think I come up with a slide that should give a decent intuition on this. Also, yeah, so fix is the one that defines all the kata m, ana, and then all the other ones that we saw in that PNG. So by the way, for a few of you that might be interested in the theory, fix here is what you might see in the literature as being called the Y combinator, and it's said that fix of draw is the fixed point of the draw functor, because basically by sticking a type parameter in draw, we made it a functor. So hopefully this should give a decent intuition. So let's say we have a fix of draw f, which is our draw, and we call unfix on it. Then what we're getting is a future. Oh, and here I didn't want to do pattern matches or make it more complicated, but basically, if you call unfix, strictly speaking, you would get a drawback. But I'm assuming that you would then pattern match and figure out that it's actually a future match f, which is a trivial thing to do. And so we end up with a future match f whose a is a fix of draw f. Okay. And then what we can do on that future match f, we call the left-hand side. And what we get from the left-hand side is a draw f. Is a fix of draw f, because future match f, its a is a fixed draw f. And that, its left and right side were the a's. Kind of wish I had the definition of future match f up there right now. And then, so we get the left-hand side, which is a fix of draw f. Once again, we can call unfix on it. And once again, we get a future match f, a fix of draw f. We can do the same thing. We call left. We get a fix of draw f. And in this case, the interesting case, we call unfix on it again. This time, though, instead of getting a future match f, we get a match f of fix of draw. And then the interesting thing here is, even though the a of match f is fix of draw, it doesn't really matter because our match doesn't have any a's in it. So we can access the left-hand side, which is a participant, or the right-hand side is a participant. So we've kind of hit the end of our tree here. So this is kind of how it works. The two data structures creating this concrete thing. Anyway, I don't know. Who thought this was helpful here? A few people. So we have a bunch of people that are like superstars, and this was not useful at all because they totally understood everything before, and a bunch of people that are really confused. There's a question over there?
To be able to write this, did you need to know the depth of the tree?
Yeah, here I'm assuming that it's a 3. The actual value is a 3 deep level, because if it was more, then we would continue getting future match f's. This is just showing how this like seemingly infinite data kind of comes to an end. That's what I was trying to do, but I didn't do a super good job. And the last thing I just wanted to mention on how this all works is we do require an instance of functor for kata. And this is just showing the signature and the implementation of kata. This is from the Matryoshka library. T here is actually fix. Matryoshka has more than fix because there's actually different Y combinators that you can use. Fix is just the simplest one. And so here T would be fix, or it could be new or mu. And our F here would be the draw. So it's a little bit scary at first, like why? But and this is the simplest one. They get way scarier. But anyway, but just to show that you do need functor. But Haskell will automatically derive functor for data types with a single type parameter, and it's pretty easy to define it in Scala. So it's not a huge requirement. And it allows you to do way more than just functor would allow you to do. Okay, so briefly talk about the benefits, or at least the ones I perceive. So I think it's great because it allows you to generalize recursive algorithms. So you're defining catamorphisms, anamorphisms, all the other transformations that we saw one time on fix, and then all your data types in your code base, as long as you define them in this style, you get to use all these recursive algorithms on these data types. The other benefit that it has, which is actually quite interesting, is it decouples how a function recurses over data from what the function actually does. So interestingly, in our first example, where we're counting the size, we were doing a top-down recursion. We were doing a top-down, tree traversal. And that's just because that's the most natural thing to express recursively. But with recursion schemes, you can define what you want to do. You ultimately want to get the size of the whole thing, and you're saying how to do that specifically. But you can actually write versions of ANA that are of anamorphisms that are not necessarily top-down. You could do them bottom-up. And so you're kind of decoupling. On fix, you can define bottom-up searches, top-down searches, and then just declare what you actually want to do, and then you could use either one. Whereas if you were kind of like hard-coding in the initial, well, using the traditional way, you kind of choose whether you're doing a top-level or bottom-up when it's kind of intermixed with the actual logic. So that's really interesting. And then the last point is avoiding general recursion. So if you do judicious use of fixed point style and recursion schemes, most transformations that you're going to do on your data, you can use the functions that you already defined on fix, if not all of them. And basically you're using general recursion one time in fix, and you're not ever using it again on your data types, which means that it means probably less chance of infinite loops and stuff like that could go wrong when using general recursion. So a few more examples now that you understand exactly how it works under the cover. So this one I blatantly stole from a blog called Some Type of Way. And I figured I'd do this one in Haskell since I've been favoring Scala so far. And so here we have an expression for a language. So indexing into an expression, calling function, like a unary function, binary, parens, and literals. And here we want to define a function called flatten, which takes an expression, returns a new expression, of which all unnecessary parentheses, or all parentheses, I'm not sure, are removed. And so we can see the implementation here. Pretty straightforward. If it's a literal, it doesn't change. If it's parentheses, we just remove it and call flatten on the inside of it. If it's an index, we basically return an index back where we call flatten on the two expressions inside of it. Same thing for call, unary, binary, pretty basically just like traditional recursion. And here's what it looks like in fixed point style. So now we defined our expression with a generic A, polymorphic A. I'm not a crazy expert in Haskell. Notice that we had to ask it to derive functor, which I believe requires a Haskell extension.
Derived functor.
Say what?
Derived functor.
Right, yeah. And then, so now our implementation looks considerably simpler. All we need to do is, so here this term here is our fix that we had in the Scala world, and the in is kind of the like unfix. Well, yeah, it is kind of unfix. And so what we need to say here is, if we get an in of paren of e, then we return e, and then we say anything other, just do the general recursion. And so we just really have to specify exactly what we're doing, which is removing the parentheses. The rest is done for us, because term understands recursion basically. Oh, I thought that I'd put I was hoping I'd put a comparison slide, but anyway, I think you can all see that it's considerably simpler than this side. Yes.
What is in?
So in is the data constructor for term. It's basically the same thing as the unfix over there. It's the type of it's the value of term, a value of term. So here I took an example from Quasar that I kind of liked, and it's got a lot of stuff going on, but it's really not that complicated, and I could have simplified it, but I wanted to show that this is actually essentially what we have an example in Quasar. And so here we're trying to do a simple in-memory evaluation of a logical plan, which is it's an AST that's traditionally used for database in modeling database like queries that you want to do. And so we get our fix of logical plan, and we want to return the vector of data that should come out of that plan, modulo a file system error that's in the in-memory FS monad. Sorry, that's just like what it is. We call optimize. That's not super important to what I'm trying to show. Also, we use the state monad to grab the memory, the current memory. Also not super important. The nice part is I wanted to show the paramorphism because it's a slightly more involved transformation that kind of shows some of the power of this technique. So we have our opt-lp, which is also a fix of logical plan, which allows us to call this para. And so what para does compared to anamorphism is the A is actually both the original data and the computed value, the original value and the computed value. And so when you're pattern matching, you get access to both what the initial structure and what you've computed so far. And in this example, it's actually quite useful. So here we're pattern matching, we're saying that if our AST node is a read node of some sort for a path, then we use our file lens to access the path from the memory, and we get our data back, and that's just the leaf, right? We get the data. If it's none, it means that our memory didn't have that file. So we return a file system exception, but basically we're just accessing the data. This is the leaf, the pretty simple part. But then we have our invoke f node, and I put the definition of invoke up there. So it's a functor, which is like a name, basically, for the function, and then a list of values, which are also logical plans. But since we defined it in the fixed point style, it's a list of A. But since it's a fixed logical plan, it's a list of fix of logical plan. And so we're saying that if the function is drop and it's got two arguments, then we want to do this this function. And so the left hand side is the original value, and the right hand side is the computed value. So here, since initially we were dropping from some collection that was just an AST, but the source here is actually the computed value. So we've already done a recursion. We have the source, we have the data, but the argument, it doesn't make sense to compute what's the data that comes out of the argument. We just want the initial value of the tree. So we have our fixed constant f of data int, because that's what we expect. And so anyway, it's just interesting because the A is a tuple of the old and the new, and so we can just, the first argument we don't care about the old, the second argument we don't care about the new. We're getting what we really need. We call flat map on it, and anyway, basically we just drop a certain amount of elements from the data. Take is the exact same thing. And anyway, the rest is not super important. But it's just showing how powerful this can be to basically be able to replace the values of A in your recursive structures with whatever, and just showing an example of probably the second simplest fold. By the way, this is what the para definition looks like. And here I actually hard coded the teeth of fix to make it simpler. So basically it takes a fix of whatever your recursive data type is, and it takes a function from from your data structure of a tuple of fix of f and A, and then you need to produce an A from that, and ultimately it's going to produce an A. Any questions on that? No?
Can you go back to slide?
Sure.
So I don't see you have mentioned on a tuple in the body of the para expression. I see you have mentioned directly on readf. Isn't readf, or isn't the position there somewhere you should be actually matching on that tuple of fix f and A?
I'm not sure I understand the question.
Can we go forward again?
It's not a tuple, it's
Oh, I see. It's a fix f and then second argument. Okay.
Yeah, the yeah. Okay. So finally, how you can use them? Well, Slam data, our backend is in Scala, so we've published this library called Matryoshka, which is fairly extensive, and so basically defines all fix and new, and so fix and all these transformations are already defined. So you can basically pull in this library, start defining your data types using fixed point style, and have access to all these recursive functions that you can use to transform your data. And if you happen to be using Haskell, there's a recursion scheme library written by Edward Comet, which is this one. And ours is based on his, although there are differences, and they both have their advantages. So finally, I want to acknowledge Patrick Thompson, who is the author of this blog post, An Introduction to Recursion Schemes, which I highly recommend. It's a really good way to perhaps familiarize yourself even more with the subject. And there's actually a follow-up blog. I think there's a part 1 and part 2. Anyway, I just want to acknowledge because I stole a lot of stuff from that blog in order to make this presentation. Also, Greg Fa, who is one of my coworkers at Slam Data and who is the main author of Matryoshka. Ed Komet, who is the author of Recursion Schemes in Haskell, which came before Matryoshka, and I think was somewhat responsible with maybe surfacing this back up, even though it's been here for a long time. And finally, John DeGoes, who's our CTO at Slam Data, who allows us to use these techniques and is very supportive and is more than willing to let us publish this as an open source project so that everyone else can use it, which is not always the case when working in organizations. So that's it. Thank you. Are there any final questions? Yes?
Could you say how this could compare to writing a traversable instance like Recursions?
Say that again?
Like how it might compare to writing a traversable instance for your data?
How does this compare?
Yeah.
So it offers more. So actually, interesting thing that I didn't mention before is all the M versions of these transformations actually require traverse, whereas the non-M versions require functor. And traverse is just the same thing as functor, but it allows you to kind of bind over the monads. So functor just provides map, whereas anamorphism, all this stuff is providing more. So it's basically, the way I see it is you define this pretty simple operation on your data structures, and you get like a lot of stuff for it. All these transformations, not an instance of functor or traversable would not or traverse would not be sufficient to do them. So their implementations require functor and traverse. So it's kind of the basic thing that you do need to do for every one of your data classes. But it provides you way more than just what they provide. And the instances are so simple that it's automatic in Haskell, and in Scala it's just take your A. It's like trivial, right? I mean, you can take any A, so just apply the function to it and reconstruct your thing. Does that answer the question?
Yeah, I guess I'm just thinking if you have to write a traversable instance, you would use the M versions, then the traversable instance would already give you a full length or something like that.
Yeah, it'll give you the traverse implementation, but it's not going to give you Anna and Kata and Para and all this stuff, which is rather useful, I think. Any other questions? Okay, well, thanks you, and hopefully you will go and make all your data types fixed point style.